it's necessary. Okay, using the fundamental theorem to solve an initial value problem. I said initial value problem, what does that mean?
We're finding a point of interest.
A particular solution, and that means that they usually give us a point in some shape or form. So now in this one, they write it a little different. For example, number 4, they say find a solution of f prime equals
Oh, excuse me.
e to the negative x squared, and then it says it passes through when f of 7 equals 3. Now this is an initial value. It's not really an initial value, but it's a value problem. What this is saying right here is that the point 7, 3 exists on the line. Okay? Now we could use the fundamental theorem of calculus because really we're looking for the antiderivative. To find the solution of this, f of x should equal the antiderivative of this. Right? Does that make sense, sort of? So if I integrate that, well, how do I integrate that? Well, one way to do it is they give us the point 7, and I know what it'll equal. It'll equal 3. So what I could do is I could evaluate it. We know that if I evaluate from 7 to 7, when my upper limit and my lower limit is the same, the area under the curve is 0. Right? So if I evaluate f of x at 7, this should equal 0. In other words, if I evaluate this at 7, it should equal 0, but it doesn't. It's supposed to equal 3. Okay? It's supposed to equal 3. So one way to work around that is I need to think of it in terms of this. It's really e to the negative t squared plus 3, right? And I suppose if I wanted to be real fancy, I'd say dt plus 3. That's what that is. That has to be that. All right. Well, if that's the case, then and f prime is equal to e to the x squared by the fundamental theorem of calculus, then what we could do is pick some arbitrary value and see what we would end up with. Okay? And so another thing that we want to consider, and I kind of skipped over this, it almost seems too simple because really f of x of 7 to some value x of e to the negative t squared dt has to be plus 3 as well. So I could arbitrarily choose any number that I want to evaluate that upper end. For example, the textbook says, well, why don't we do this? If that's the case, then f of negative 2 should equal the integral from 7 to negative 2 of e to the negative t squared dt plus 3. Now I can just integrate this if I wanted to on my calculator and get an answer. Because that's really all I'm interested in is the answer, and then go from there. So what I could do is I could go to math and then choose option number 9 and just evaluate the function. Now I put this in math print so you guys could see this. I'm going to say 7 to negative 2 of e to the, e to the negative t squared. So I'm going to say negative, and I'll just say x, and I'm going to square that. And then I'm going to take the derivative with respect to x. Now you could put t's, but I just didn't feel like plugging it in the calculator. So now all that's going to do is calculate the area under the curve, which is this, right? So it's negative 1.76 something. So this right here, all this stuff here, is negative 1.76, and now I just need to add 3 to it. Okay? So if I'm going to add 3 to it, let's go back to my calculator. Now if I just add 3 to it, I'll get like this positive number of 1.217. So what I've done is I've calculated that f of negative 2 is actually approximately 1.2317. Okay? Any questions on that?
So that's it? That's the answer?
That's it. So it says find the solution to the differential equation of this, this, and this. And so now to find the solution to that, it doesn't really find the solution for us. So I'm not quite sure I like the way that it worded the question. Really what it just shows you is how the fundamental theorem of calculus could be applied. The key to this is that we had to figure out this plus 3. Okay? Now, truthfully, there is a way to figure out what, if I take the derivative of something, I'm going to get this. But what they're saying is, in the real world, if I wanted to find, this is usually an application. So if I know that this f prime represents the rate of change of some other function, and I'm interested in other words, what is f of negative 2, right?
Mm-hmm.
See, I don't really necessarily need to know what f of x is, as long as I have some process to evaluate f at some value of x.
So how do we know which x to evaluate it at? Like,
You could arbitrarily choose anything and you would get a number.
But I mean, for like homework wise, do you think they'll give it to us? Or like, I could pick 5 and the book's like, why didn't you do 2?
Oh, I see what you're saying. Well,
Like, how do we know to like get the right, or is this just showing us how it's done?
well, what you would do, and you wouldn't do it for your homework. There's a couple answers to the one question you have, because really you have like 2 questions in one.
Okay.
First one I want to do is clarify is what is it example 4 wants us to do? Example 4 wants us to find the solution of the differential equation.
Okay.
F prime equals e to the negative x squared. Now, the truth of the matter is that it's not easy to find. There's some chain rules, and we have e to the x. I mean, that's not an easy function to find the derivative of it. So one way that we could do it is take the antiderivative, and I'll do that later. There is a way to do it, and I'll show you that later. For now, let's just assume that it's too hard for us to do. Well, the solution is necessary for an application. In other words, they might want to know what is f of 5. So they give you f prime, and they want you to find a particular solution, which really means what is f of 5.
Okay.
All right? So what you need to do then is they're going to give you f of 7 or f of 3 or f of something. Let's just do one from the book and I'll show you, okay? So it says now try problem number 21 from the textbook. So let's just go to problem number 21. And 21's written a little differently. It says, find the solution of, this. So this is 21 out of your textbook. dy dx is equal to sine of x squared, okay? And then it says that y is equal to 5 when x is equal to 1. So that means that the point 1 comma 5 exists on the line. Okay? So what we want to know is what is y? Well, y, based on the fundamental theorem of calculus, is just the integral of sine of t, right? dt, okay? And so from here what we would do, we would evaluate that from 1 to 1. Now we know that when the upper limit and the lower limit are equal, that the area under the curve equals 0, right? So really, essentially what we're solving for is what is y of 1? Well, y of 1 is supposed to equal 5, right?
Yeah.
So the equation y of 1, we want to rewrite this as some sort of variation of x. Y of 1 is really this plus 5. So my equation is really y is equal to, using the fundamental theorem of calculus, this is supposed to be squared. That is the function. Ta-da, we're done. That's it. So this is the function.
Mr. Adams.
Yeah.
Why is it still sine? If sine's the derivative.
It's not sine, it's the antiderivative of sine squared. Sine t squared.
So the antiderivative of sine squared is sine squared.
The only thing that's really kind of throwing you off is we don't know what this is. This is some function. We just haven't gone through the work to figure out what that function is. Right?
No, I'm pretty confused. Why didn't we take the antiderivative? Isn't that what we're supposed to do?
Not in this case.
Wow.
We can, because that's not what they're trying to teach you. What they want you to do is have practice. What the purpose of this question is to practice the fundamental theorem of calculus.
But
And
doesn't it only work when you take the antiderivative?
apparently it doesn't. Apparently you could do it another way. This is a workaround, right? Sometimes in the real world, we may know what the rate of change is, which would be the derivative, right? So let's just recap. You're asking great questions. Try to stick with me and we'll figure it out together. But this represents the rate of change of some behavior, right? Well, all the problems in your textbooks, it's rigged. So you can easily find the derivative of antiderivative. But in the real world, it's not easy to find the antiderivative. So let's assume, it's not true, but let's assume I'll never be able to find the antiderivative of that. Well, I still want to know what y is,
Okay.
okay? Because what if I want to know what y of 2 is? What if I want to know what y of 3 is? Well, y of x is going to be this thing evaluated at whatever. So the answer is all this stuff right here. This is y. This is the solution. And this stuff in the blue circle represents a smaller function or expression. We just don't know what that expression is. But I can calculate a numerical value of it using my calculator. Does that make sense?
I guess.
Let me do one more example, and I think it'll help.
Did you solve it? Like, are you?
That's it. We're done. That's the answer. Let me show you.
I don't like that at all.
All right. So let me show you. Let's start with something simple. I've got dy dx is equal to 2x minus 3, and this goes through the point . Well, give me a second. Let me let's just do this. So we've got dy dx equals 2x, right?
Mm-hmm.
It says find the particular solution. So find the antiderivative of this. Now, if we use that same approach, we would say that y of 2 is equal to because this right here, when the upper and lower limit are the same value, the area under the curve is 0, right?
Shouldn't you put dx?
Yeah, we should put a dx in there if we want, okay? But it isn't equal to 0 because when x equals 2, y equals 4, right?
Yeah.
So the only way I can get 4 is I've got to tack on this plus 4 at the end. Now, what does that mean? That means that my function y is equal to the integral from 2 to x of 2t dt plus 4. This is my function,
Okay.
okay?
So then how do you know when to take the antiderivative and when to just do that?
Well, we don't, well, okay, now wait, we're not done yet. I'm not done
'Cause,
explaining it to you.
2x, we could easily take the antiderivative.
We could. But what I want to show, that's not what I want, just pay attention and be patient with me, okay? Now, if I wanted to know, do I know y of some x? Like, this is complicated because we haven't solved that by finding the antiderivative, right?
Mhm.
But we all know in reality, because Mr. Adams specifically chose a simple equation, we all know that this represents y equals x squared, right? If we take the antiderivative, y equals x squared. So, what is, if I take y equals x squared and I let x equal 3, what should my y value be?
Sorry. 9.
9, right? So I'm saying that this is the same as x squared, right?
Yeah.
All right, so now let's do something on the calculator. If I want to know what y is evaluated at 3, I would do something a little different. I would say math integral, and I'm going to go from, what was it, 2 to x. So we're going to go from 2 to x, so I'm going to say 2 to 3, right? Because we're going to let 3, that's what we're interested in. And then over here, I'm going to put 2, and I'm going to plug in t on purpose, I think, if I can. Where's t at? RT. There it is. Oh, I didn't want y, I want a t. Alright, so I'm plugging in t on purpose, and then I'm going to make it of dt. Plus 4.
Okay.
Now when I hit enter, what should I expect?
9.
9. Boy, I hope that works out right. 9.
Okay.
So what I've done is, now I know that 3 squared equals 9, and we did it on purpose, but essentially, I've solved, I can figure out what y of any value is by plugging it into this. Pick another number, 5. If I let x equal 5, then what will y equal? 25. If I take that the same setup, and I go math, and I go from 2 to 5, and I'm just going to plug in the x now that you guys kind of know what we're doing, of x, and then I say plus 4, I should get 25. So I may not have, this isn't written the same way, but these two mean the exact same thing. Mathematically speaking, they will get me the same answer. This is the same as this.
Okay.
And that's all they want you to do. They want you to write it like this, though. They want you to get the practice of doing it like that. Okay?
Okay.
Now what the answer in the back of the book, what they're expecting you to do is this right here. And that's it. You can stop there.
Okay.
And the example that I showed you was really just trying to show you how you would apply that in the real world.
Okay.
Okay? Good question. Does that make sense now?
Yeah.